All right, Chapter 8 test review session. So, taking a look at this, again, all things dealing with matrices, basically. Again, we've got a few problems here, excuse me, intended to help us prepare for Monday's Chapter 8 test. So, first thing, skip the slide here. First thing we want to jump into, again, we want to write the system as an augmented matrix. So, first up, again, writing this out as an augmented matrix, we need to make sure to do a couple of things. Number one, is that we need to turn this into a 3x4 matrix. Again, we have three equations, and we have four columns that we need to build. And we need to build an x column, a y column, a z column, and also the constants column. So stealing the coefficients here, we're going to go with 1, -3, -5. Again, this is augmented with the coefficient matrix. So 1. The second row, we must fill in zeros here. So 0, 1, -2, 5. Again, must fill in zeros for the x and the y terms. 1z equals -1. So you might recognize that this augmented matrix is already in, it's not reduced, but it's already in row echelon form. Again, if we wanted to solve, again, we could, I don't want to say easily, but we could fairly quickly get this into reduced row echelon form. So before doing any of that stuff, it's going to ask us what is the order of the augmented matrix. Again, I think that I already mentioned that. 3 rows by 4 columns is what we're looking at. And then now, again, we can actually solve this thing. So we're asked to perform the elementary row operations to the matrix to get it into reduced row echelon form. Again, currently we're in row echelon form. We want to get into reduced row echelon form, which means that we need to turn zeros into the 3 values that are above the +1 diagonal. So again, we want to write out this solution to this system. So first thing I want to do is to just copy the augmented matrix that we just created down. So again, that was 1, -3, -5, 1, 0, 1, -2, 5, and 0, 0, 1, -1. And this was augmented, looking something like that. So my target is going to be at -3. That's what we're shooting to turn into a 0. Again, typically we work down the first column, then up the second column, and up the third column. So as is the case with almost every rule, there are exceptions. So again, making certain that that we understand that you're not always going to follow that completely into perfection. That's again merely the suggestion, merely the generality that hey, that's typically what we're going to try to do. So back to this though, specifically, if we're going to target row 1, column 2, that tells us again we're going to be altering or changing row 1, or we could think of it this way, that row 2 and row 3 will stay the exact same. So 0, 0, 1, -1. Again, now the adjustment that's about to be made, I have a -3. I need to turn that into a 0. So if we think about how we can change a value from -3 to 0, there's really only one way to do so. I have to add the opposite. So the opposite of -3. I have to figure out a way to add +3. So with the combination of another row, how could I add +3? So I'm going to have to take 3 times row 2 and add that to row 1. So looking at my row 2, again, multiplying it through by 3 and then adding it up to the previous row 1. 3 times 0 is 0, plus 1 is still 1. 3 times 1 is 3, plus -3 is now 0. 3 times -2 is -6, plus -5 is now -11. And let's see, where do we go from here? I guess 3 times 5 is 15, plus 1 is 16. All right, so our first column is complete. Our second column is now complete. So going back down to the beginning of the third column. Again, we normally would jump down here, but we're good. We have the +1 where we want it, so now we're just going to move up the column. Now we're targeting that -2. So now we're targeting row 2, which again means that row 1 stays the same. Row 3 stays the same. Now, if you're watching me do this, or if you've worked ahead, I don't know how exactly you prepare for your test with this podcast, but again, maybe you are looking at this and saying, well, I targeted that -11. I don't know what he's doing. You can still be successful by going, like we said earlier, slightly out of the order that I'm going. So, again, please don't worry about that. I promise you we're going to get So if I am targeting that -2, again, I have -2, I have to turn it into a 0. The way that we turn numbers into zeros is we have to add the opposite. So again, this is going to be now 2 times row 3 plus row 2. So 2 times row 3. All right, so there's row 3. Doubling that is 0 still, plus 0, 0. 0 plus 1 still 1. Now +2 plus -2 is 0. -2 plus 5 is 3. The last value that needs to be targeted, again, is our -11 in row 1. So again, we have rows 2 and 3 exactly as we want them. So I'm just going to copy them down before I accidentally change something. And row 1, again, is about to be changed significantly. So again, we have -11 in row 1, column 3. I need to have a 0 there. So what we are about to do is take 11 times row 3 and add that to row 1. So in doing this, again, multiplying row 3 times 11, so 11 times 0 is 0, plus 1 is 1. 0 plus 0 is still 0. +11 plus -11 is 0. -11 now plus 16 is +5. So we have successfully altered this 3x4 matrix to where it is now in reduced row echelon form. Again, we have positive 1s on the diagonals, 0s below and above. And now, again, if we were truly completely changing this back over into into system of equations, we would say that we have 1. This way, hopefully this was successful previously. If we were looking at this as 1, 0, 0, 5, 0, 1, 0, 3, 0, 0, 1, -1, what we're truly saying is that 1x plus 0y plus 0z is equal to 5, 0x plus 1y plus 0z is equal to 3, 0x plus 0y plus 1z is equal to -1. But of course, we would never, ever write the system that way. Again, we would write the system this way, where we could say that, yeah, 1x is equal to 5, 1y is equal to 3, and 1z is equal to -1. So once we have this format, again, with x, y, and z, we have our 5, 3, -1 ordered triple that we can obtain for our final answer. All right, moving on then to the second set of problems. Again, as you can see, we've got let's see, problems 2, 3, and 4, following matrices A, B, and C. So first thing we want to do is to understand when is it even possible to obtain these. So really how it breaks down is that if we are adding or subtracting matrices, remember we have to have the exact same order. If you are multiplying matrices, that's when you're going to have to match. The number of columns of the first has to equal the number of rows of the second. So no matrix multiplication here other than scalar multiplication in this second problem. So if we're looking at this, if I run a scalar of 2 through C, again, 2C, I'm going to do this in blue here, just literally multiplying all 6 terms times 2. 0 times 2 is still 0, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times -2 is -4, 2 times -5 is -10. There is 2C, plus, we're about to do the same thing with matrix B. So again, 3B. So all 6 elements, again, multiplied through by 3. 3 times -3 is -9. 3 times 9 is 27. 3 times 4 is 12. 3 times -1, -3. 3 times 8, 24. 3 times -6, -18. So the first question that we need to ask ourselves is, can we add these together? And the answer, of course, is yes. I have a 3x2, or plus, excuse me, a 3x2. Both of these matrices have the exact same order, therefore we can proceed and add them together. So now it's just a matter of row 1, column 1, plus row 1, column 1. So 0 plus -9, -9. Row 1, column 2, plus row 1, column 2, 4 plus 27 is 31. We're going to continue with that. 6 plus 12, 18. 8 plus -3, 5. -4 plus 24 is 20. -10 plus -18, -28 for our final 3x2 matrix. So continuing on here, now we want to actually do the matrix multiplication A times B. So when we multiply A times B, again, it's going to be wise for us to test before jumping in and actually doing any math. We should test to see if we can actually pull this off. So I know that matrix A is a 3x3 matrix, multiplying it by matrix B, which is a 3x2 matrix. Again, 3 rows, 3 columns times 3 rows, 2 columns. I think I said that back. 3 rows, 3 columns times 3 rows, 2 columns. So what we're noticing, hopefully, is that our middles match. So absolutely, yes, we can multiply. And furthermore, we know that we're going to obtain a 3 by 2 matrix. Now, the reason why that's significant is the way that I've, all along, all in Chapter 8, have encouraged you to do these problems, is to build the 3 by 2 matrix to start. And we need 3 rows, 2 columns, looking something like this. And now we're going to go about actually trying to calculate. So when we multiply A times B, again, when we're looking at this for exactly what it is, I'm going to target, again, row 1, column 1. So when I'm looking at row 1, column 1, that means I literally take row 1 times column 1. So first element's here, 1 times -3 is -3. Second element's 2 times 4 is 8. Third element's -3 times 8 is -24. Now moving over, row 1, column 2. Row 1 times column 2. Again, first element's 1 times 9 is 9. 2 times -1, -2. -3 times -6, positive 18. Moving on, row 2, column 1. Row 2, column 1. Again, this time in our multiplication, again, just working right down the row. Let's see, we're going to get -15 plus 12 plus 32. Row 2, column 2. Row 2, column 2. Again, now we're going to get 45, -3, -24. Row 3, column 1. Row 3 times column 1. So the -6 times the -3, 18. 1 times 4 is 4. -4 times 8, -32. Row 3, column 2 to finish this thing up. Let's see, first element's the -6 times 9 is -54. The 1 times -1 is -1. -4 times -6, positive 24. So we're almost through. We're almost finished. Now we actually just find the sums. Hopefully what we view is the easy part. We already know that we were shooting to obtain a 3 by 2 matrix. So row 1, column 1, I'm adding those up to get -19, positive 25, 29, 18, -10, -31 for my finalized 3 by 2 matrix. All right, then number 4, kind of the same thing. We have 7 times A plus 2 times C. Now, we could jump through the hoops and actually, scale through the 7 and scale through the 2. But at the end of the day, I know that 7A is going to be a 3 by 3 matrix. And I know that 2C, again, the scalar isn't going to adjust this. 2C, that's going to be a 3 by 2 matrix. I know that these orders are not the same. Therefore, we cannot add them. So this sum does not exist. There is no solution. It is not possible. All right, moving on. Number 5. Now we want to write the Gauss-Jordan, we want the, I can't apparently talk or read right now. That's going to be problematic. Let me try this again. We want to write the system of linear equations as a matrix equation, AX equals B. Then we want to use the Gauss-Jordan elimination on the augmented matrix in order to solve for our matrix. Okay, whole bunch of lengthy wording going on there, but basically what we need to do, again, starting out with the matrix A times X equals B. A is going to be our coefficient matrix. So 2, -5, 3, -8. Times our variable matrix, which in this case looks like our variables x1, x2. Sometimes we have x and y, but again here we have x1, x2. And then we have our constant matrix that appears to be A1. So lots of different ways to obtain an answer here when it comes to systems. But what we want to do is we want to look back to this that we've just created. A times x is equal to b. If the goal is to get x by itself, I can't divide by A, but I can multiply by A inverse. So that's what we're going to do, is we're going to multiply by A inverse, which is causing the cancellation. So now X is going to be equivalent to A inverse times B. So this is what we're going to attempt to do. We already know that this is matrix B. Again, we've got that. We already know that this is A, this is X. So what we really have to do is, in our next step, is to figure out what A inverse is, so then I can multiply it times matrix B. So I'm going to stop the podcast here, and we'll do that on the next.